Okay, welcome everyone to lecture number 12. I hope that you had a good spring break. So let's get started right away. Okay, so just a brief recap of what we have done so far. Yeah, this one. So we are still with the problem of operator learning, and oh, this was too big. Operator learning, and we look at this abstract PDE, which is right here. And this could be any differential equation, right? It could be your ordinary differential equation. It could be a stochastic differential equation. The stochastic partial differential equation doesn't matter. The main point is that the the sort of the problem setup itself, the setting itself. So the target, what we are going to learn, is this guy here, G, the operator, and this maps a function space to a function space, right? So it takes the inputs to the PDE, in this case, the coefficient A and the source F, and it produces the solution U. So this is the setup that we are in. And just to recall from the last lecture, that we cannot parameterize. In particular, what we can't do is we cannot work with, let's say, finite dimensional subspace or a small parametric finite dimensional subspace of the space X. We really have to work with something which is infinite dimensional in some sense, or at least a large finite dimensional subspace. Okay, so with that setting in mind, let me remind you what we tried to do to solve this problem, right? So one way we thought we could solve the problem was as follows. So we started with the input, for instance, this is the vorticity field in the Navier-Stokes equation. So this was here, the vorticity field in the Navier-Stokes equation. And we sampled it on a grid. You can see that the grid points are there. This was a 16 by 16 grid, but in practice, it's a 64 by 64 grid. And then we applied, you could have an MLP, but we applied a CNN, so different layers of the CNN. And that gave us a finite dimensional output, which was also on in this particular cartoon, on a 16 by 16 grid. So you take a vector, which is 256 dimensional, and you produce another vector, which is 256 dimensional. So that was the objective. And then we could interpolate, right? So interpolation led us to an infinite dimensional, back into an infinite dimensional space. So if you do that, then of course we think that we solved the problem, but the reality is that we don't solve it. I mean, this was the main point, for instance, in this graph here. As you can see, at the training resolution, we got satisfactory results. But as soon as we changed the resolution, we got into problems. So this was the whole point of my last lecture, that you are not learning a function to function mapping. What you're learning is a particular finite dimensional approximation to finite dimensional approximation mapping. So you are only learning something at the discrete level and not at the continuous level. But since we're dealing with functions, we have no choice but to work with the continuous spaces, right? Function spaces. Whereas because of computation, we have to work with the discrete. So that's why it's important to enforce some form of discrete continuous or continuous discrete equivalence, right? And towards the end of the last lecture, I tried to sort of introduce that. Maybe I was a bit rushed. So what I'm going to do is to start by recapitulating, recalling some of the concepts and perhaps explaining them better. Okay, so how do we sort of formalize and formulate this continuous discrete equivalence? So we do so with this framework, which is called ReNO, representation equivalent neural operators, right? So this is the framework that was introduced last year from my lab. But it essentially what it does is it provides some sort of a notion, proper notion of this continuous discrete equivalence. And the key is this picture here, means this figure here is worth 1,000 words. So let me try to walk you through this figure. So our problem, let me pick a color that is not there, orange is good. So our problem is right here. So we start with a function space X and our outputs are in a function space Y. So in reality or in principle, we need to approximate this quantity, the script G, the operator, right? The object that maps infinite dimensional space to infinite dimensional space. Unfortunately, we don't know how to work with infinite dimensional spaces. We can't work with infinite dimensional objects, with continuous objects on a digital computer. So we have to work with some sort of finite dimensional representation of it, right? And this is provided by these spaces X and Y. So these are finite dimensional spaces. These could be, for instance, as you saw in this example, points on a grid, right? So the function is an infinite dimensional object. Its values on points on a grid are a finite dimensional approximation. And then, of course, there is a link between the infinite and the finite. And these are provided by this encoding. So let me recall. So this was an encoding. This is E. This goes from the infinite to finite, right? And reconstruction. As the name suggests, this is a mapping which takes you from finite and back to infinite, right? So this is the setup that we are in. So of course, what you would ideally like to is to connect the two, right? You want to say that when I go back from the infinite to the finite, go from the infinite to the finite and go back to the infinite, I don't make an error. And this is sort of conceptualized or formulated in terms of these aliasing errors, right? So these are the key objects here, aliasing error. And it's a very, very automatic error. Means for those who are more mathematically inclined, all that we are asking is for this diagram here, this guy here, to commute. How does that happen? So let's try to understand it. Remember that there are two ways in which we can go from x to y, either directly by the operator g, which is what we would ideally like to do, but in practice we would not be able to do that, or we can go from the infinite to the finite. So this is, for instance, taking the function and putting it as point values on a grid. So we do this through this E here, right? Then, so we come here, and then we use the whatever the MLP or the CNN that takes the finite dimensional values on a grid to values on a grid. So this is this step here, and then we try to go back to the infinite dimensions. And to do that, we have to use this R here, right? So we come down like this, we work like this, and go up like this. So this is a very, very simple construction, and this is the composition here. And ideally, by doing this, by coming from infinite to finite, working in finite and going back to infinite, we want to be exactly able to approximate the operator G, or exactly able to realize, represent the operator G. And this, if you don't do so, if you make an error, and this is precisely what is the aliasing error, this is an operator because it acts on operators, and this error has this functional form, right? So it essentially says that by going through this route, what is the error that I'm going to make? As long as it is 0 per layer, remember that I had this layered construction because neural networks are layer-wise. You'll see several, at least one prominent example later today. So if I did not have this layer, if I make an error at one layer, of course this error can grow, right? So maybe the error is only 1% in the first layer, but then it goes to the second layer, it becomes 2%, then it becomes 4%, 8%. You can expect geometric growth, right? So that can become large. So we want to stench it. We want to sort of kill it at each layer itself. And we say that we try to have operators. So this is something that is given to us, right? We cannot manipulate that. But what we can do is we can design the E here, we can design the finite dimensional spaces, we can design the G here, the R here, such that there is no aliasing error. So this is somehow the objective, the mission that we have, the goal that we have. And once we do that, there are several goodies that come our way, but this construction is absolutely essential and sort of the core of operator learning. Is that clear? Are there any questions here? Because last time I rushed this, so I thought that I would try to explain it again. Yeah, and we will do a couple of concrete examples today. So you'll see that really hit by the pollen allergies, so I'm struggling a bit. Okay, so then what is the first goodie that drops our way? So first of all, this is structure preserving in the sense that what you do at infinite dimensions is mirrored in a finite dimensional world. So there's exact mirroring of what happens between the two. And an immediate consequence, which is something which we realized is an issue, if you remember, that once we change the grids, we were in trouble, right? So let's see what happens if we change the grids or change the resolution or representation for that matter. Then we have this picture here. So now we have in two different grids. So for our purposes here, this is more abstract than just grids, but for our purposes here, just imagine that you have two different grids, right? So you have a grid which is given by, the operator is given by G, and you have another grid where the operator is given by G prime. Okay, so now we want to connect the two. We want to say that if I train on G and if I go to G prime and I test on G prime, I shouldn't be making an error, or at best I should be making a small error, right? Ideally I shouldn't be making an error. But the point is, how do you do that? So if you have this ReNO property, if you know that there is an exact mirroring between the continuous and discrete, this is a triviality. Why is that? So remember that I want to go between G and G prime. So what do? I'll work out an example in the next slide, but let's look at this abstract concept. So I have a mapping which takes X, the discrete space, values on a grid, to Y, another discrete space, values on a grid, through the mapping G. But I know that there is an exact mirroring to the continuous. And how do I go to the continuous? I start with, so how do I go to the continuous? How do I realize this? I start with, maybe it's incorrect here. Or remember that we always have this formula here, right? Maybe it's the other way around. That the continuous is represented by the discrete in these forms, right? And similarly, I have another grid here, G prime, where the same representation holds. So I have the same representation here and the same representation here. Now I want to go from G prime to G, right? I want to use G prime and G together. So what do? I start with G prime, right? I start with G prime, but I know that from G prime, you can go to this operator G here. And how do I do that? First, I use this R prime. So to go from here to here, then I use this mapping, and then I can come back. So this is the mapping which is given here. Okay, straightforward. But I know that this mapping here is given in this form. So in order to realize this mapping, I go back through here to the finite dimensional space X, use G, and come back. And I compose the two. Okay, when I compose the two, so to go from G prime to G, what I do is first, I go from X prime. This is the discrete space. So let's say resolution on a grid. First, I go, so this is the operator here. I go to my infinite dimensional space here. And then I go to this finite dimensional space. So this is this block which expresses that. I work with this finite dimensional space, which is given here. And then again, in order to do so, I go back to the infinite dimensional space, right? And come down. And this is the formula which is given here. And remember, because this diagram commutes, whether you use the direct evaluation or whether you use this, you get the same answers. Okay. So this is a very, very simple construction. You just compose these two diagrams. And once you compose these two diagrams, you know how to relate two different discrete representations. Because as I said, in practice, if you remember in the last lecture, I also had a picture about it. You don't have means there could be multiple discrete representations, multiple grids on which I can represent the function. And the way in which I relate them, I will do a concrete example in a minute, is precisely through this construction. That you start with one particular grid, go to the continuous level, and then come back to another grid, and then come back. You see, so this is the way in which you can move between grids, and then it's a sort of very elegant way of moving between grids. Any questions on this? Let's work out an example just to sort of concretize. Also, people on Zoom, if you have any questions, don't hesitate to ask it in the chat box. Okay. So let's do an example just to realize this in some concrete, these constructions in some concrete manner. Okay, and then we will check for different architectures whether this holds or not. So I just take a very, very simple example. 1D, this can be done in multi-D, there is no issue there. And let's take a picture. So let's take, so this is 1D, let's say this is a unit interval. And let me draw some picture of a grid. Just for our visualization, like this, you can't have a grid with 3 points, but just for our visualization. So we have, this is the discrete representation. This will be my grid G. And what is my continuous? So usually whenever you're given functions, these functions belong to some Sobolev spaces, some spaces of continuously differentiable functions, twice continuously differentiable functions, and so on. So to realize these constructions, these function spaces are too big. So we have to work with, let's say, smaller function spaces. And this is well justified, okay? This is well justified. In most cases, at least for PDEs, this is well justified. So instead of working with this very complex spaces like square integrable functions, what we're going to do is to look at infinite dimensional subspaces of them. And the space that I introduced last time is a space of band limited functions. So what are band limited functions? These come from signal processing. Just for simplicity, I mean, this is not a rigorous definition by any means. You know that any function, let's say periodic function, u of x, can be written as uk sine k pi x for simplicity, right? And all that you do is that you truncate the number of frequencies to some capital K. Okay, so you have a function, you expand it in sinusoidal basis. We'll look at the Fourier transform later, but let's say for simplicity, you have a Fourier basis representation. Okay, and then you expand it in the Fourier basis, and you just say that the high frequencies beyond a point don't matter. Of course, this can be suspect because some functions have lots of frequencies. But at some level, there is only white noise, which has equal content in every frequency. And that's why it's white noise. If you have any structure in a function, what you know is that beyond a certain frequency, the frequencies are going to decay. So essentially, I can sort of throw them out. We'll see a rigorous version of this argument, not in the next lecture, but in the lecture next week. Okay, but so this is the first step, that we are going to deal with functions which have finitely many frequencies. Could be 100, could be 200, you know, something large, but in practice, it's probably less than that. So in other words, the support of its Fourier transform. So essentially the support of the Fourier, this is the Fourier series version of that. The Fourier transform version is that it is sort of compactly supported within some band, right? So here the Fourier series is truncated beyond a certain point. So these are band limited functions. And this is a particular example. You could think of some other functions, and these corresponding operators are going to change. Now, what is the encoding in this particular case? So this is given now. These are band limited functions. The encoding in this particular case, you can work with pointwise evaluations. So you take a function, so whatever function that you have, just an example, and you just take its values in the grid. So you take this value, the value here, and so on. Okay, so this is the values in the grid. So this is the encoding. And what is the reconstruction? So encoding takes an infinite dimensional object, a function, which is given in green here, and represents it by a finite dimensional object. So in this case, just a 3 vector representing the values of the points. Right? And then to reconstruct the function, we have to go back from something which is finite dimensional back into the infinite dimensions. And this is done by, in this particular case, by using what is called a sinc basis. So all of you should know what is a sinc function. So sinc of x, I could get the constants wrong here, but morally it is sine of x by x, right? So this is roughly sinc function. And then what you do is that if you have been given finitely many quantities, Vj, so you take Vj, so this is the values in the grid, and then you just form this basis expansion. So this is the sinc basis, right? And as long as your grid is dense enough, so let's say that your cutoff frequency is k, right? And if the number of points is twice that, or a little more than twice that, then you have a very famous theorem from signal processing, harmonic analysis, which is called the Nyquist-Shannon theorem. What it tells us that whether we work with the function itself or whether we work with the values in the grid, there's a one-to-one correspondence. Okay. So how many of you know about the Shannon theorem? Everyone should know somehow, right? So all that it says is that if you have a dense enough grid for these band limited functions, then you can represent it just by the point values in the grid. But if you don't have a dense enough grid, then you get what are called classical aliasing errors. Okay. I usually have a picture, but now I don't seem to have this. So the picture is if you take sine 3 pi x and sine 20 pi x, and if you don't have enough resolution, these two functions will agree at many points. So you cannot distinguish between them, right? It's very easy to read it up. For instance, on Wikipedia, there is a nice article on this. So the setup is very clear. So you have a bijection. Bijection means 1, 1. Everything is sort of equivalent. There is a complete mirroring. provided that you are in this setup. So this is band limited. These are values on the grid. This is the sync basis. This is just the point values, taking the point values of a function. And you can do the same at the output level. So you can also do the same at the level of this grid. Okay, so now aliasing error is just computing what is going to be the difference between these two, because R, E, these are all okay. So all that you have to do is to ensure that your G is such that this quantity is identically equal to 0. Okay, so this is a straightforward task to check. And another way to think of it is how this program is realized. What happens when I move between the two grids? So let me try to explain this a little bit. So let us say that I have a G, which is a ReNO, which is alias free, and it has taken values, or it has been trained on these 3-point values, just for simplicity. Now let's refine the grid, right? Let's take the black here. And let's take some additional, why didn't this work? Let's take some additional points. Let's take these are your new points, right? So how do I evaluate this? How do I know that this is going to work out? So now remember that my input now are values on the new grid. So the values on the new grid are the squares as well as the circles, right? So this is the new grid, squares as well as the circles. So this is a finite dimensional object, right? So the first thing that I do is that since it's a finite dimensional object, I want to go to infinite dimensions. How do I go to infinite dimensions? I use this basis here. So I have a finite dimensional object. Let me call it as V1, V2 up to V7 in this particular example. I go to infinite dimensions. I know the positions of these points. So I go to infinite dimensions using this sync basis. No problems. I'm assuming that my density in both cases is enough so that the conditions, the Nyquist barrier is satisfied. I can represent the functions. So now I am at infinite dimension. This is a function. And then remember that I have to project back to the original. So the original grid is just these 3 points, this guy here, this guy here, this guy here. So I have this new function, which is infinite dimensional, and I can just evaluate it at these 3 points, right? So I evaluate the function at these 3 points. So I just, these 3 values here. Then I use my operator, the neural operator that I have designed, this G here. This will give me the value again at these 3 points, right? So it takes 3 points, it goes back to 3 points again. No problem. So this is a finite dimensional operation. And then remember that I have to go back to my new grid. So what do? I again go back to my infinite dimension by this reconstruction. So now I have been given some new values here. Let me call them as V hat 1, V hat 2, V hat 3. And once I have this, I again use the sync basis, go back to infinite dimensions, and then I evaluate them at these new values. That's all. I evaluate them at all of them. So in a way, I'm performing sync interpolation twice. And then I'm completely, there is complete fidelity here between the infinite and the finite dimensions. And then I can realize that this formula tells me that this error is going to be 0, ideally, okay? If your construction is solid, this error is going to be 0. So this is a concrete way in which you can evaluate, you can go between grids. That you start with a particular grid, 7 points, construct the function. Of course, you are never going to construct actual function because that's an infinite dimensional quantity. There's no point in doing that. Evaluate it on the new grid, or on the old grid rather in this particular case. Do your operation, which was anyway trained on the old grid, go back again to the infinite dimensions, and then project back to the new grid. Okay, so this is a systematic procedure in which you can go between these spaces. And this also explains to you how this link between the infinite and the finite dimensions works in practice. Okay, so is this example clear? So this was precisely I did it in a manner so that you can understand this particular construction. So my suggestion is afterwards, go home, try to understand this. And if there are any questions, you can always ask me in the next lecture. Okay, so let's move on. And this tells us that, first of all, the starting of the story was this particular guy, right? Which somehow has the same flavor, but there is something which is missing, which is this continuous discrete equivalence. And then, of course, we realized that I did it very quickly. That's why I'm repeating it, because I felt that one needs a proper explanation. So the first thing was, of course, the fact that CNNs, as we expect, these are not ReNOs, means this is, somehow I'm not able to change. What does that mean? Remember that CNNs are nothing but discrete convolutions. So you have been given a signal, which is on the, let's try to expand this a little. How does it look? Because for me, it's very difficult to see when it's in small print. Okay, so as you can see, so you have signal, which is given on a grid. So this could be band limited functions for simplicity, right? And then what does a CNN do? It doesn't do this sort of complicated gymnastics that I just explained. That's why it doesn't work, of course. But what it does is that it always has this convolution kernel, which is given by some K. Okay, so graphically, I'm representing this by this kernel here. Okay, all that it does is that it, so there is a window. So for each point, it just multiplies these 3 points, gives you a value, then it moves on. At the next level, it goes to these 3 points, then these 3 points, and so on. So this is the way in which CNN works. And what is being trained during the training process is, of course, the kernel, right? Because the coefficients of the kernel are what are unknown to us. And these are the things that are being trained. So the kernel is fixed. Now, when you go to a new grid, so as you can see, this grid is a refinement of the grid, just exactly in the sense that I did before. This is a refinement of the grid. I have added a few points. I can also reduce points, means that's equivalent. And again, I'm assuming that the density of the points is such that this Nyquist condition is satisfied, and there is there is some bijection essentially between the continuous and the discrete. Now, what happens? So I have this trained kernel. This is the training process. I train the kernel, and I want to evaluate it on the new grid. Convolution makes it very simple. You don't have to do any fancy things. I take the trained kernel, and I just keep on multiplying with the new points. Okay, so I take these 3 points and I multiply. Now I change the color. Then I take these 3 points and multiply, these 3 points and multiply. I have a trained kernel, so there's no, this just evaluation. This can be done very, very fast. But now you see what the trouble is, right? So the trouble is that if I just focused on this point, I just have to focus on one particular point. Okay, let's use the black here. So let's focus on this particular point. So for the grid, this coarse grid here, my convolution kernel would have multiplied these 3 points, right? Now for the same grid point, which is here, this would have multiplied these 3 points. It's the same kernel, but it's multiplying different points or values at different points. And of course, the signal's amplitude is different at these points. It's a smooth function. So these are not very, very different, but they are different. So what does it mean? That per evaluation, since you're not doing all this gymnastics, you're not doing this interpolation automatically, what happens is that you get different values, right? So you definitely have different values when you multiply with these 3 points or with these 3 points, right? There is going to be different values. You make an error. Yes.
If you use some sort of straight convolution proportion to the change in scale.
This is what we will do later, as you'll see. This is an important point. You have to resize your convolution kernel in some automatic manner. Otherwise, you cannot. But with the CNN, the picture that I produced, I was not doing this, right? So this is the essential point that is to be remembered. So here I was not doing this. I was using the same kernel and I was just windowing it across. I can do it. No one stops me. People were doing it. And then you see what the effect is going to be. So now, because of this thing, you make errors and you see what you see. So there is a resolution dependence here. There is no resolution independence. And as a result, CNNs they're neural operators in the sense that you can always take an infinite dimensional object and you can map back to infinite dimensions. That's straightforward, right? But the fact that they don't have this structure preserving property means that they will make aliasing errors and these things will accumulate, right? So this is a very, very important point that we should remember. So essentially, I repeated the contents of the last lecture but I needed to do so. I realized that I was too quick. Okay, good. Any further questions on this? So this doesn't work. So our first approach that we used doesn't work. So what are we going to do now? So let me introduce some alternatives. So in the next few lectures, we will look at different kinds of alternatives. And I'll already start with an alternatives that you have seen in your tutorials, because tutorials are a little ahead, because next Monday there is a holiday. So eventually we will catch up. It has been done on purpose. And also I'm teaching very slowly. So anyway, so the first alternative that we are going to deal with is what are called neural operators. And they have been around for everything here is fairly recent, right? Like 2-3 years. They've been around relatively long in this time scale, right? So they were introduced, at least formalized by a group in Caltech. Nick Kovacsky was the first author. And the idea is extremely simple. The idea is also elegant, right? In some sense. So what you do is the following. Remember that what are neural networks? At the end of the day, neural networks are compositions. Remember that this is my definition of neural networks. These are compositions of different layers, and each layer has a particular structure. And the particular structure is, it takes a vector y, right? And it outputs another vector. Let me call it as z, zk in this particular case, so zk plus 1 or something like that. So it inputs a vector, potentially a high dimensional vector, and it outputs also a high dimensional vector. So this is the sort of mode of operation. And the operations within each layer are very simple. This is do a matrix vector multiply. So you have a matrix vector multiply with a weight matrix, add a bias vector, and do a nonlinear activation. So these are the three things. We have a bias vector, a weight matrix, and a matrix vector multiply, and a nonlinear activation function. And you keep on doing it, and so on. Of course, there is more structure to it in general, but this is the simplest construction that you can imagine. So the contention of these authors was the following, that if you want to work with infinite dimensions, all that we have to do is to generalize this construction to take as inputs and outputs, not vectors, but functions, right? Because here, everything for a neural network, it's vectors input, vectors output. All that we have to do is to take function inputs and function outputs, right? And this is what it does. It is also a composition of layers, as you could expect. And each layer now, for simplicity, I just mapped the function space to itself, but there is nothing sacrosanct about that. So you take a function space, you take a function, and you get out a function. Let's say that I take a function v, which belongs to x. I take my script n, which is a layer-wise neural operator, and I produce a w, which also belongs to x. Just for simplicity, it could belong to a y, but it belongs to x. So this is the basic construction. And in order to realize this construction, we have to find analogs, we have to find extensions of the following objects. So instead of I have to generalize a bias vector to infinite dimensions. This, as you can imagine, will be pretty straightforward, right? We have to generalize the weight matrix or the matrix vector multiply to infinite dimensions. And we have to do the activation function in infinite dimensions. If I can provide these ingredients, then in principle, I have extended something which is essentially a finite dimensional construct into infinite dimensions. Everyone agrees with me? This is a very straightforward sort of a thing. And how we do this, of course, is where the action is, where the fun is, right? So let me just try to explain to you how we do this. The first thing, remember that there are three ingredients. I have the bias vector, I have the matrix vector multiply, and I have an activation. So remember that now my n, okay, this is NL, but let me, for simplicity, I don't even know why I put an L there, but let me put an N here. N is a mapping which takes function to function. So my W is equal to N of V. Okay, so this is the setting that I'm going to work with, that I'm working with the matrix, I'm working with the function input and a function output, right? So of course I need a bias, I have to replace my bias vector with a bias function. And this is straightforward. So instead of having a bias vector, you just add a bias function, right? So instead of a vector, just take a function. Of course, in practice, we have to deal with large vectors, but this is a function. The harder part is what happens to the matrix vector multiply. Okay, so here we need a little bit of thinking, but not too much of thinking, because essentially what we do with the matrix vector multiply, I have to write a few things here, is that let's think of it. So remember that I have A of y, remember this was A of y, which is of course pointwise. So A of yi is nothing but summation of aij yj, right? So this is what a matrix vector multiplier looks like. Now, what would be an infinite dimensional analog to it? In infinite dimensions, what would happen is that this object, okay, maybe I give you the answer and then you see why it is an infinite dimensional analog. So infinite dimensional analog to a matrix vector multiplier, which is given here, is given by what are called kernel integral operators. Okay, and they are given by this object here. So now remember that I don't have a vector, I have a function, right? So my function is given by a v. So I take the function at each point and I multiply it with a kernel. Okay, so kernel, of course, by definition has two arguments, x and a y. So just like you'll see what is the analog in a second. So you have x and a y, I multiply this and I integrate over y. So then I get a value wx, right? Or w bar of x. So it's a way in which I can use a linear operator to go from a function to a function. And why is this an analog? Of course, it's an obvious analog that you just have to use a quadrature. Let's even do Monte Carlo quadrature, right? So Monte Carlo is the simplest. You just take some random points in D and you're going to approximate this object here. You're going to approximate it by 1 over m, summation of j from 1 to m of k of ij. Let me write down k of ij vj. And what is k of ij? K of ij is nothing but the kernel at xi yj, and vj is nothing but v of xj. So you take point values on a grid and you take the values of the kernel on a grid, then you get precisely this form. So now you can see that this is precisely the same form as before. Of course, we have a scaling factor, but we can push the scaling factor inside, right? So the discrete version of a kernel integral operator is precisely a matrix vector multiply. Okay, so if you have a matrix vector multiply and you want to work in a function space version of it, that is a kernel integral. So this is also obvious, means it takes two lines here of argumentation and all of you are convinced, this is the right infinite dimensional analog, right? So this is a very simple infinite dimensional analog. Good. So we have replaced this by the bias function, this by the matrix vector multiply by the kernel integral operator, and then we are left with just one ingredient. Remember that there were 3 ingredients in a simple neural network. The third ingredient is the nonlinear activation. Now, the simplest thing you can do here is just pointwise activation. What do I mean by that? So if you have a function, okay, let's directly work with it because then we are sort of running out of time. So this is the affine part of the neural operator, right? So now all that you have to do is so now if you evaluate it at any point x, you can evaluate this. You can evaluate b at that point and you can evaluate this integral at that point. All that you do is to act on this pointwise. What does it mean? So take these values, let me call it by a w. So psi of w is nothing but acting at x is nothing but sigma acting at w of x. So you evaluate the function at any point and then apply ReLU, or evaluate the function at any point and apply the hyperbolic tangent or swig-LU or geg-LU or whatever, the entire zoo of activation functions that we have. So voila, you're done, right? So you have an infinite dimensional generalization of neural networks. All that you have done is you have replaced the bias vector by a bias function. You have replaced the matrix vector multiply by a kernel integral operator. And you have replaced you have not even replaced it. You have just realized the activation pointwise. So you have an automatic recipe of how to construct these objects, right? So where is the catch there? So what are the learning parameters? They are in this BL, means this is a function, right? We have to learn this function and we have to also learn a kernel, K of L. So all the learning parameters are hidden here. But once you have done that, you do that from data, you have a neural operator. So this was the contention of these people, right? It turns out that there is a little caveat, even for the realization of these things, because at the end of the day, how are we going to store a function, right? We can't store functions. We have to sort of store them in some finite dimensional representation. How are we going to compute the integrals exactly? We can't compute integrals exactly. We have to use a quadrature and so on. So there are some computational issues with this construction. But in terms of just the construction, in terms of just an abstract framework, this is very nice, right? Because it provides you a very simple one-to-one correspondence between neural networks and, let's say, neural operators. But after the break, what we're going to see is what are the difficulties here? Where do we get stuck? Okay, and we start from there. Okay, so let's meet at, just for simplicity, let's meet at 10 past. Okay, 10 past, so 12 minutes is enough, I think, as a break. We are sort of running out of time otherwise. Let me pause the recording. Okay, so welcome back, and let's see how we realize these things in practice, right? So now, so what is the computational realization of these objects? So per layer, you already see the issue, but let me explain it. So at every layer, per layer, so I will not give you the layer index, I will simply give you the final answer. So NV of X was given by sigma, this is activation. Then you have some bias, P of X, plus the matrix vector multiply. K of XY, V of Y, dy. Right, so this is how it is at the level of functions. But in practice, we have to work with discrete objects. So of course, we have to work, the simplest thing is to work with grids, points on a grid. So instead of V of V, the function V, what we can do is we can work with point values, which is completely fine. If you have band limited functions, for instance, J from 1 to, let's say, N, right? So this is, these are the values. Similarly, K, the kernel, which is a two-dimensional function. So K will be approximated by, so let's do this, Kij, which is K of, okay, this is Yj, sorry, K of Xi, Yj, right? And now I and J are from 1 to N. So, okay, so this is the throughput here, and similarly for B. So B of X is going to be approximated by Bj, which is B of Xj. So we have replaced the functions by these discrete vectors, and we'll replace the integral with a quadrature. So integral of D of K of Xy By dy can be approximated by summation over J, some weights. So these are the quadrature weights, omega J of Kij. So this is Vj, right? So this, and then the finite dimensional realization. So NV at the point I, so this is the grid point I, is given by sigma. So it looks very much like a neural network, right? Except that there is one little catch here. So this is Bj plus, or Bi, sorry, plus summation over J of omega J, Kij, Vj. The omega is just the quadrature weight. This could be 1 over m, for instance, if you do Monte Carlo sampling, right? So the J is from 1 to n. So n is the number of grid points, or the number of points that you have. So what is the computational cost of going from one function to another function, right? So the computational cost would be, so this is I is from 1 to n, right? So for each I, how many operations do you do? So at least of the order of n operations. So the total is of the order of n squared operations. Now, what is this n? N is the number of grid points. Number of grid points. And this in particular is given by some m to the power d, right? So in one dimension, you just have 10 points. In two dimensions, it will be 100 points, 10 squared. In three dimensions, 1000 points, and so on. So the total operation count is of the order of m to the power 2d. So it grows exponentially in dimension and it's quadratic, the growth, not linear. So in some sense, you can see that already there is this is an issue that we have to deal with, right? Because we have a big cost of computation. So just imagine that you're in 2D, which is the standard thing that we often deal with, and you're doing processing on a 100 by 100 grid. Okay, so this is a grid on which you have the inputs and outputs. So now you have 10,000 points, right? And the computational cost is going to be 10,000 times 10,000, which is 100 million. So per layer, it is going to be 100 million. And if you have 10 layers, it will be a billion operations. And this is already on a very, very small grid. This is just the basic number, right? Because you also have to evaluate the bias vector. You have to do this, you have to do that. The very basic number is already a billion operations for a very, very simple network. And that's unaffordable very, very quickly. And this is also not necessary, right? So we need to have some basic structure. So this is why I explained this particular caveat, which is that there is a computational complexity, a large computational complexity, which is inherent because it's essentially taking MLPs into infinite dimensions. And you know, the reason why we don't work with MLPs in finite dimensions is because in general, they have other issues with them, but they have computational, already at the baseline, they have serious computational complexity issues. Right? Some people have suggested different kinds of operators. We will look at many of them. So for instance, there are what are called low rank neural operators, graph neural operators, multipole neural operators, and so on. There's a whole zoo of these objects which try to confront this computational problem head on. How do I do a compression? How do I go away from this quadratic cost? And arguably the most successful version of it is something which we have already seen a bit of that in the tutorial, but this is what we are going to look a little bit more closely and a little bit more deeply. What are called Fourier neural operators, or otherwise called as FNO. So this is widely considered to be, let's say, the most, let's say, popular, at least of all the neural operators that are there. It has been around now for a few years, very well cited and so on. So what are the structural properties that it uses? And I'll give you a little bit of detail here so that you understand what's going on. Of course, you have also implemented this in the tutorials. Okay, so what is the basis of Fourier neural operators? So the key here, as one of you suggested to me during the break, is that this kernel is what this kernel integral operator, which is this matrix infinite dimensional analog of the matrix vector multiply. This is the bottleneck, right? Because this is where this quadratic cost comes from. So how can we sort of solve that problem? So the first thinking about it, which is also how CNNs came into being in the first place, is that there is no reason to consider general kernels. Okay, so the first condition is what if we do a translation invariant kernel? So translation invariant kernel gives you a special structure of the kernel. That the kernel, this is exactly what happens in CNNs. So you have a translation invariant kernel now, which is given by k of x minus y, right? So, and the inductive bias here is that a lot of the inputs and outputs that you see in physics are translation invariant. So this is automatically, at least in this particular form, it's a motivation, right? So now this kernel, which was given in this general form here, is precisely a convolution because this is k of x minus y, v of y dy. So it's a convolution. Okay, we're back into CNNs. We could have also used convolutions there, right? But the key trick what these people came up with is that, so convolutions automatically reduce the cost, right? Because now instead of a dense matrix that is being multiplied, you have a sparse matrix which is being multiplied. So this is somehow the key trick. But now what they said is that, okay, instead of performing convolution in physical space, why don't we perform it in Fourier space? And you'll see that there is a payoff because we saw what was the issue with convolution at the beginning of the lecture, right? So by doing it in Fourier space, you do overcome some problems. And to do anything in Fourier space, we have to work with the Fourier transform, right? So what is the Fourier transform? If the function would have been just periodic, I could have just used Fourier series. But here it's, in general, you have to work with the Fourier transform. The Fourier transform script of f is a mapping which takes the function, okay? It takes a function and it churns out the frequencies. That's roughly what it is. So now I have given it in some generality, in some detail, or in some, because my point is that these functions, they are defined on domain D, right? And they are, okay, Fourier coefficients are complex valued. So we have taken the general, in generality, you have taken complex valued functions here, but they need not, means the imaginary parts could easily be zero. So this is a generalization. Whenever you work with a Fourier transform, one typically works with a complex valued functions, but they could be real value. And the key here is that these are vector functions, okay? Because just imagine that the air outside, the features are not just given by the temperature, the pressure, the wind velocity, humidity, precipitation, whatever. So these are vector functions. So just to keep the generality. And the J now here is giving the vector index here. Okay, so you can also think of J as not being there, everything being a scalar. But I have to present things in a little bit of generality. So the Fourier transform is given in terms of what is called the trigonometric basis. So this is the complex exponentials, sines and cosines, because in general, you cannot rule one out or the other. And then what you do is that you take the function, which is square integrable at the very minimum, so that these integrals are well defined, and you churn out the frequencies. And the frequencies are defined on a lattice, right? So the D is the underlying space dimension. So the frequencies are defined on a lattice. And the kth frequency, so the k is a vector now, it's a D vector, is given by just taking the function, multiplying it with the kth trigonometric polynomial, and integrating. But this is just a Fourier transform. All of you have known this since analysis 1 or 2, right? So everyone knows. All that you do is to represent the function in terms of its kth frequencies. Now, there is you can get back from frequency space back into physical space by using the inverse Fourier transform, F inverse. So this is a mapping which takes values on a lattice. So just let's take the two-dimensional version of it, right? So the frequencies are discrete. Just these are integers, right? We don't take continuous frequencies, these are discrete. So let's say that this is one frequency, this is another frequency, and so on. So you have been given the values of the frequencies and you want to reconstruct the function. All that you do is that you take the corresponding frequencies and you form the sort of the basis expansion with the trigonometric basis. So there's a one-to-one correspondence between physical space and frequency space. You can work with one or you can work with the other. And the idea behind what these people, it was Zhongyi Li from Caltech, who was the first author in this paper, what they essentially proposed is to work with Fourier space. So we do many things in Fourier space. You know, there are numerical methods, spectral methods, which work in Fourier space. So why not use them, right? And this seems to be very successful in different ways. Let me explain that. So now the basis is the fact that we do convolution in Fourier space, right? So there's a cartoon here or a representation, but let me try to explain what really goes on here. The most important thing, let's see if I have the space to do it. Generally, I clutter up all the space, but let's see. Okay, so remember that at the end of the day, I'm carrying out my convolution K convolved with V in Fourier space. So all of you know that when I take the Fourier transform of a convolution, what happens to that? So Fourier, yeah, multiplication. Very good. So this is the one thing I remember from my harmonic analysis classes, is that this becomes a multiplication. So this is in physical space, this is in physical space. In Fourier space, this becomes a multiplication. Now I want to come back to physical space. What do? I take the inverse Fourier transform, right? So you take the inverse Fourier transform. So this means that I have F inverse of f of k times f of v. Okay, so now this is the throughput here. So sorry. So of course we have to do it. We have to realize it at a discrete level, and this I'm going to tell you in the next slide. But now, just for the sake of argument here, just for the sake of understanding, let's think that we can work with functions, right? If we can work with functions, so what do? I take a function, I compute its Fourier transform, okay? Then I do a multiplication with a kernel. This kernel could be it could be in physical space, but I can also do it in Fourier space. Who stops me from doing that? So this I will write as a, this I'll write as an R here. So this guy here, I'll call as an R. So this is just a Fourier multiplier. I do this. This is a learnable object. And then I take an inverse Fourier transform. And this is precisely, so remember that this thing is this layers, layers, layers. So these are these Fourier layers. And let's unroll one of these Fourier layers. So you take a function, you take its Fourier transform. There is a trick here that I'm going to tell you in a bit, but when we do the discrete realization, so what the Fourier transform does is that it sort of gives you different frequencies of the function. You multiply this Fourier multiplier, you get back some frequencies, and you take some inverse Fourier transform. So that is sort of the basic workflow here, right? So once you do this, then we have nonlinearity. We have the bias vector. So you bias vector is just this b of x, right? You just add it. So that's nothing special about that. But there are a few additional tricks here that let me explain to you. So the point is that we have to parameterize the kernel in Fourier space. And this bias vector is not that important. Let's for simplicity today, let's set it to 0. Let's focus on what is important. So we set the bias vector to 0. It's a bias function to 0. This can be readily added. There are 3 additional ingredients that give the power to this method. So these are this P here, okay, this Q here, and the W here. So the P, and I'll explain that in a second. These are very easy operators to explain. So this P is what is called a projection. Q is what is, no, other way around. Okay, so P is what is called a projection. Brain is, my brain is not, because my brain is simply not working. Lifting. Q is what is called a reconstruction or a projection. This is their notation, not mine. I would not have used this notation, right? Because it's sort of non-intuitive, but I want to be sort of have some consistency with the code. And this W here represents a residual connection. All the symbols are sort of not nicely done, but this is from their paper, so I sort of state residual connection. Maybe in the next version of the course, I use my own notation. Okay, so what are these lifting, projection, and residual connection layers? They are very simple. So let's start with P. So P is essentially what is also called a channel augmentation. So remember that my input is a vector function, right? In general, it's not a scalar, it's a vector function. So V is a mapping from D to, let's say, Rn. Okay. So what the P does is just a linear in general. You can make it into an MLP. Some people use an MLP, but the simplest version of it is it's just taking P takes this mapping V and it produces a PV. Okay, PV is a function. So PV belongs to, PV is in R. Now I'm out of notation. Let me call it as some M, where M is much bigger than N. So in other words, it takes, let's say, pressure, density, velocity, and so on. So these are the natural variables in which we describe our system. These are the features. And then what it does is that it says, okay, who says that the machine learning algorithm will use the same features? Let's endow it with some additional features. These additional features may or may not have any physical representation. Typically, they don't have any physical representation. So you take a vector, which is 4-dimensional, your input, which is 4-dimensional, physical, or 1-dimensional, let's say temperature, which is physical, and you take it to 100 dimensions. I'm just giving a number. 100 is not that uncommon, right? So this tells you that already from the data, we are equipping it with some additional features, some additional channels. Okay, it's very common in image processing where you take RGB, but then you suddenly expand it to, I don't know, 12 channels or 16 channels, 128 channels. This is a very common trick or a very common realization. Intuitively, it says that we don't know what features the machine learning model is going to use in its algorithm. So let us provide it with the possibility of additional features. Okay, so this is what this lifting operator does. It takes the input and it lifts it to a, let's say, not a higher dimension in physical space, but in feature space. Okay, so it's a feature space lifting. And projection is just the inverse of that. So you lift it to a high dimensional feature space. You do all your processing in a high dimensional feature space, m dimensional feature space, and then you want to come back to your physical space, because at the end of the day, I only have information about my temperature, pressure, density, humidity, things like that, right? So projection is just the opposite. It takes W, which belongs to Rm pointwise, and then it produces Q of W belongs to Rm. M and N. Okay, so these are this lifting and projection operators. These are linear. They are learnable, right? We are going to learn them during the learning process because we don't know what are the features. If you knew, then that would be the point about machine learning, is to have as little human crafted and as much end-to-end learned features as possible. Okay, so this is a way to automate that. It's very, very common in computer vision to do that, and some of these features I can have a scientific intuitive interpretation, but I don't need to. Okay, and the last point, is that clear what we do with this? Very simple, just a matrix essentially, discretely. We will see it in a second how this is done discretely. It's just a matrix, and then we do the processing. Okay, and then what is this one here? This is a residual connection or a weight matrix essentially. Let me write it down. So remember that you have the sigma, you have your convolution kernel, which is done in Fourier space now, right? V of y dy plus, now this is the fun part of it. So this is W of V of x. Okay, so you take each point and you have a learnable representation. This is like a essentially a residual connection. This is a parallel route. Here is all the processing which is happening. Here, no processing is happening except for keeping some information from the previous step. Okay, so that's why it's a residual connection. In machine learning, it's useful to have these residual connections so that you have better gradient properties essentially. And it turns out we have done some analysis of this, that this particular map here is very, very important. Okay, so this is again linear, does not depend on space at all. It just depends on the features, right? So you can, some people also call it as channel mixing, because all that you're doing is that you're mixing up the different features together in some form, right? So this is FNO at a continuous level. So what do? I take a function, I've set the bias to 0, that's not important. I keep I mix some of the features of this function locally at each point in space, means, so this gives you some global information somehow, right? Because all the points are the same, let's say the same constant that is multiplying, the same matrix that is multiplying. And then I do things in Fourier space. I take Fourier transform, do a Fourier multiplier, take an inverse Fourier transform, add them up and pass them to the nonlinearity. And I keep on doing it, right? So how is the processing done? You take a function, you take your input function, you add channels to it, do the Fourier processing and the residual connection, Fourier processing, residual connection, Fourier processing, residual connection. At the output, project it back to your original feature space and you have your answer. Okay, so this is how it is done at the level of functions. This is a very simple architecture in some sense, and we will see that these computational complexity caveats that we had, these are somehow very nicely resolved because we do things in Fourier space. There's one trick here, which is that we need to compute the Fourier transform and we need to compute the inverse Fourier transform, right? We've been given a function. Of course, we do it pointwise. So we have to compute a discrete Fourier transform and a discrete inverse Fourier transform. So this, all of you know, can be done very, very fast through FFT, right? So we have the fast Fourier transform and the FFT does this. If you are on a grid, for instance, equispaced on a grid, this takes you n log n operations. So this is a very, very fast operation. Okay, so is that clear? Are there any questions about how FNO works? Yes, James.
So as far as the FNO in the Fourier space, cuts out some high frequencies.
This is what I'm going to describe exactly in the next slide. So again, good anticipation of what I'm going to do, because I've still not given you the discrete recipe yet, right? This is all at the level of functions, but I need to sort of translate it at the level of actual vectors, so great values, right? So that is what, because I want to sort of explain it. And I don't have to explain every piddly little detail because some of these are very obvious and then you understand. The thing that is the most important here is to work with the Fourier layer, right? This Fourier processing layer. I'm recording. Yeah. Okay, so let me try to precisely raise or address the point that James raised, and let's try to understand this at a discrete level. So what do we do? And again, I just look at one layer. I'm assuming that this. Okay, let's try to explain this. That's why I have a whole slide blank so that I can fill it up. So remember that I have for each Fourier layer, so that you understand what's going on. So for each Fourier layer, and now I'm not going to use a layer index L anymore, right? So this is the same across all layers. So my input, if it was a function, would be given by some v of x, right? So this is a function. But in reality, I have a discrete input, which is Vj, which is P of xj, and this j runs from some 1 to capital N. So these are points on the grid, because at the end of the day, we have to work with points on the grid. There's no escape from that. And remember that for each j, Vj is in some, it could be complex value, but let's keep things simple and it's real value. This is in Rm. Rm is this high dimensional feature space, right? So I have lifted to this high dimensional feature space, and I'm processing along this high dimensional feature space. So I've been given this vector, but since this vector itself has many features, I can write it as a m cross n matrix. For in implementation, it is usually done as a m cross n matrix. Then I do the Fourier transform, right? So the next step is, okay, so let's take the Fourier transform. So in principle, if you remember, and this was why James, I think, asked the question, so the Fourier transform allows you to evaluate any frequency. So if you want the 1000.1000 frequency, it can do. If you want the million by million frequency, it can do, right? You can evaluate any frequency. In practice, you cannot do that because that would be an infinite object and we have to make approximations. So what kind of approximations can we make? We have to cut it off, right? So this discrete Fourier transform is, so you have a discrete Fourier transform. Okay, so you take this Vj's and then you take, now I'm running out of notation, but let's try. So V hat, because Fourier transform is always given, but this is V hat of k. So this is the discrete Fourier transform f of Vj. Okay, so you have values on a grid. You take the Fourier transform of this matrix. And then what you do is that you have minus capital K less than or equal to little k less than or equal to capital K, because you have both positive and negative frequencies. So you take this. So in other words, what you do is that you take a signal and you cut it off into frequencies, okay? And typically, the idea is that this 2k plus 1, so these are the number of frequencies, capital K, is less than, it could be much less than the number of points, n, okay? So this is somehow the key to the computational complexity as well as the working. It need not be, but then you pay more in terms of computation. And evaluating this Fourier coefficients is fast. This is the fast Fourier transform, right? The complexity is quite nice. So you take it and you do some truncation of the frequency. And this is what they express here, that you don't need all the frequencies, you keep only some of the frequencies. You could also do that by taking a matrix, which is R, which is a multiplier matrix and having a lot of zeros in it. But the simplest conceptually is to think that you take a signal and you, let's say the signal is on a 100 by 100 grid, but you don't have to keep frequencies 100 by 100 frequencies. You see, you can keep 20 by 20 frequencies. And this is sort of the, in some sense, a key point here. So this is the Fourier transform. Then it's the Fourier multiplier. So this matrix now is 2k plus 1 by 2k plus 1 times 2k plus 1, much smaller, of course, times whatever m features, right? So you have all these frequencies in each direction, and then you have m features. Then you have Fourier multiplier R, which is going to take these values and I made a mistake. Give me one sec. It's 2k plus 1, of course. 2k plus 1 times m. And then this Fourier multiplier matrix, you really do it in terms of a tensor. So it takes it and it takes, so essentially it takes C of 2k plus 1 and it produces a complex number which is 2k plus 1 for simplicity. It could be something else. So it takes 20 frequencies and it transforms them into 20 frequencies. It could transform it to 30 frequencies if you want, or 15 if you want, right? So there is this is learnable. So this is the part which is learnable. And in the code, it is realized as a tensor. And then you have the inverse Fourier transform. Inverse Fourier transform. I have to keep some look on the time, otherwise I'll be in trouble. Okay, so you take the inverse Fourier transform, and then the weight matrix, you have this W matrix multiplication. That is trivial, right? Because now you just have a point-wise matrix that just mixes up the features. So essentially, the key here is that you do a Fourier transform through FFT, which is very fast. You truncate it. You only take only few frequencies. You do the remultiplication with this Fourier matrix. Then you take the inverse Fourier transform, add it to the residual connection, and you keep on processing it. So the cost is, you see several places where we have reduced the cost. We have taken FFT, so that bit is very efficient, and you have taken much smaller, but smaller sort of frequency compactification of the entire thing, so that there is also a source of efficiency. And then we keep these things in parallel. And this is sort of the somehow the key to this particular feature. And anyway, you have seen this construction in the code during the tutorial. Good. So any questions on the implementation of the FNO? Because this is an important baseline that we will also consider in the exercises. Yes. Usually, that's a very, very good question, right? Usually it's a hyperparameter. And it's sort of, there is a ballpark. There are people have done now experiments for many, many years, and somehow 24, 16, or not more than 30. You could, but no one does it. You could do it as a learnable parameter, but then it's harder, right? Because then the code becomes very complicated. You have to put several zeros. You have to pad with zeros in order to keep the. So you could write that code, but what's the point? So it's sort of there is some good theory to say that you don't need so many frequencies, because remember that some of the frequencies, it's not like you're killing all the frequencies, because just imagine that you have a signal which has many non-zero frequencies. Okay, some of it are, a lot of it is also retained through this guy here, because remember that this guy retains all the frequencies. So you keep a part of the signal, and only a part of the signal is the high frequencies are kept in some sense, and then the low frequencies are processed. So there is some additional parameterization there. Okay, so but it's a good question. 20, order of 20. Yes. Yeah. It is acting in Fourier, but it's just a matrix or a tensor. The interpretation is that it is a kernel parameterized in Fourier space, but its interpretation is purely that of implementation is purely that of a tensor, because it takes a vector of frequencies, right? It transforms them into another vector of frequencies, but then it has to be a matrix. But because each frequency has different features, it has to be a tensor of the appropriate order. Yes.
The inverse Fourier transform is equivalent to the Gromwich integral, where I have problems when the real part is negative, for instance, I have poles.
Yeah.
How do you deal with this problem?
Why is this a problem? Because
okay, when the real part is negative, it's not defined and stable there.
But if it's only for functions because these functions are typically, you are taking band limited functions in some sense, right? So you don't simply have the frequencies that cause problems. Yeah. Further questions? Good. So keep the questions coming, then we all understand better, including myself. So it's always good. So now, good. So now the point is that, And this I have to go a little bit quickly because otherwise we'll be out of time. So I'll then just end up repeating in the next lecture. So it doesn't really help maybe. As I said, these are very widely used in practice. We will see some numerical experiments next week probably. But as one of you asked, means the whole point was to construct ReNOs, right? So are these ReNOs? The answer is yes and no. It's a mixed answer. Of course, ReNO, the concept came much later than FNO, so there's no reason to. So there are two elements to it, right? So first of all, this lifting and weight matrix and so on, these are just linear operations which have nothing to do with space. They have to do with channels, and so these are by definition ReNOs, means they don't change anything in the spatial structure. So that is so the two essential things, right? So you have a convolution in Fourier space, and you have a nonlinearity. So it turns out that one can show that if you have the right spaces x and y, so in particular, if you take periodic band limited functions, pk, so this is a space of periodic functions, then there is an automatic convolution. And the reason why the convolution, let me give you the intuitive reason, and then there is a proof which is given in terms of this diagram. The reason why it works is because you do this low dimensional Fourier projection. So you might take your signal and any grid, okay? So you might take it on a coarse grid or a fine grid, but at the end of the day, what you do is that you project it onto the same Fourier modes. And as long as these Fourier modes have this Nyquist barrier being satisfied, so it does not matter if I take a 64 by 64 grid or a 128 by 128 grid. I'm at the end of the day projecting them onto the same Fourier space. I'm working with this Fourier space, so there is no ambiguity in terms of the convolution. If I would have kept that changing, if I would have changed this k with grid, then I would be in trouble. But since I don't, and this is where the proof is, because the Fourier transform, of course, is a for these band limited functions, there's an automatic relationship here. So this is in continuous. Then you're just multiplying a Fourier multiplier. So you do nothing here. And then you take the inverse Fourier transform, right? And you can just use the Fourier basis. So this T of psi k is simply using the Fourier basis, pointwise evaluations, and then you just use the Fourier basis. And these diagrams are all commuting. So this is it's a very simple argument to see why FNO, the convolution part of FNO is real. Because unlike in the previous case where I was keeping the same kernel, here because I'm working and then I was getting into trouble because I was operating in physical space, here by keeping the same sort of Fourier multiplier for a fixed Fourier space, I'm avoiding that problem. Okay, so of course the designers of FNO didn't have those considerations in mind, but this is what it turns out to be. However, it's not just the convolution, right? We also have a nonlinearity. And this is where the trouble is. And let me explain to you where the trouble is. So the point is that all this is done if you take the right spaces, if you have a right connection between the continuous and discrete. And this is provided by, for instance, band limited functions, right? Because then you know that certain frequencies can't be amplified, certain frequencies are completely damped down, and so on and so forth. Now, when you take nonlinearities, you really get into trouble. So let me explain to you why. Because let's say that you have a function which has 10 non-zero frequencies. So it has sine x, sine 2x, sine 10x, and so on. Now you take the simplest nonlinearity that you can think of, the square, right? You take the square of sine 10x, what do you get? Sine 20x, right? Because, and then of course you have started with 10 frequencies and you automatically end up with 20 frequencies. So nonlinearities, what they do is that they can break the structure. They can introduce additional frequencies. And this is where the trouble is. And this is best shown in this picture here. So I've taken a signal. Let me use black maybe. I've taken a signal which is in orange. So this is a signal. And I've applied different nonlinearities to it. Okay. So I've just used the Nyquist frequency as a barrier. Let's just focus on ReLU, because GeLU is just a smooth inversion of it. ReLU, as you can see, it clips all the negative parts, right? And it just keeps the positive parts. So this is where ReLU works. Now in frequency space, the same function. So these are the frequencies. So as you can see, I have taken 20 frequencies. My original function had 20 frequencies. But as soon as I apply ReLU, you see my original function, it remained within the frequency bands, right? But as soon as I apply ReLU, I have this leakage. You see that there is this leakage which is happening. And this leakage means that I'm introducing high frequencies. And because I'm introducing high frequencies, I break the band limits, and even if my convolution keeps them, if my convolution provides that structure, because I'm using nonlinearities which are not keeping the band limits, you end up in trouble. Okay, so even if one part of the chain works, the other part of the chain does not. Activations are going to introduce high frequencies. These are not necessarily resolved in the grid, and that causes aliasing. So this is roughly what the story with FNO is, and let me give you a couple of examples just to illustrate that, and then we finish. The first one is a very dramatic example. It's not a PDE example. In PDEs, what happens is that frequencies have some decay. That's the whole point. Very high frequencies are damped down. But this is an example where high frequencies can remain high. Okay, so it's an assignment problem. It's a random assignment. It's a perfectly kosher, well-defined operator. So what you do is that you have some inputs, which is a random field, and the output is also a random field, and you just assign different points randomly across. Okay, well-defined operator, not continuous but measurable. So everything should apply to it. And then when you train it on a particular grid, so it is trained on 61 by 61. One is because of this 2k plus 1. Okay, 61 by 61, it is 30 frequencies, and you can see whether I take the CNN or the FNO. At this resolution, they almost give no error, right? You can easily learn. And then I just evaluate the output on different grids. As soon as I change even one grid point, all hell breaks loose. So here the Nyquist barrier is not satisfied anymore. Okay, since the Nyquist barrier is not satisfied anymore, you can't expect that the errors will remain low because the bijection that we had is broken. But here the Nyquist barrier is satisfied, so we should expect that the errors are low, but they are not, right? Almost immediately, as you can see, both for CNN, because the convolution itself has issues, as well as for FNO, because here the nonlinearity has issues. You don't have the same resolution. The errors are very, very large. Of course, this problem has been constructed in order to make it extreme. Okay, so in some sense, it is a contrived example. So the nonlinearity, not preserving the band limits, leads to that issue. It turns out that even in practical problems, you cannot avoid it, even though the people who invented FNO thought that they could get away with it because the errors would be low, but that is not the case. So this was CNN UNet, but it's essentially CNN, and you remember that how the results were. So we have the mapping between the velocity and in the beginning, initial velocity and final velocity for Navier-Stokes, and this is the corresponding vorticity. So you start with some shear, and then you start introducing vortices. So if you take FNO, then what happens is that you end up with trouble, even in this part. Here the Nyquist barrier is satisfied, so there's no reason why it shouldn't be. But you can see that there are very reasonably large increases in error. Here, on the other hand, there is an increase in error, but it's not as dramatic as before, right? So it was, but it's not zero. So there is aliasing error because the high frequencies are damped down. So you can see that the error goes from, I don't know, 3.6% to around 3.8%. There is a mild growth, and if you would have continued, it would have continued growing probably in this direction. So by design, it is not a ReNO. In this particular case, it didn't lead to as many problems, particularly when you evaluated it at higher resolved meshes. But in principle, it can lead to problems, right? Because CNN, both the nonlinearity as well as the convolution broke the band limits. So of course, it was worse. So compared to CNN, of course, FNO is better, but it's not a solution. In this particular sense, it's widely used, but there is an issue. So we still have this challenge, which is to design something which is genuinely operator learning, rather than just learning maps between particular finite dimensions to particular finite dimensions. Okay, and this is what we will do on Friday, and we continue also next week. Good. So we finish a bit early, but we also took less time during the break. Bye-bye.